Hello AP Physics students, this is Dr. Brenzy again, and this is part 2 of the lesson A.4 video. And in this video I'm going to show you a couple of examples of how to apply Bernoulli's equation and the continuity equation to solve physics problems involving fluid flow. Okay, so in this first example we have air that is flowing through this tube right here. And it goes through a constriction point here at A2 and then comes out here through this section A1 and the airspeed, it tells us in this section, is V1. So let me go ahead and draw that. So the velocity in this section of tube is V1. And it says if the airspeed in section 1 is V1, what is the height h of the water in the tube? So this is water down here, and it is being sucked up into this tube up here. And we can assume that the area A2 is equal to half of that at A1. A couple other things it doesn't tell you that you should probably know. Let's see if I have those punched up right now. Let's see here. Oh, so there's V1. Let me back that up. We don't need two of those. There we go. It says that this, you can't see the small print, so I'm rewriting it here. It says that this section 1 right here empties out into atmosphere. That's what that little print said. And so what I can assume is that P1 at this point right here is equal to atmospheric pressure. So whenever you have something emptying out into atmosphere, you can assume that the fluid at that section is atmospheric pressure. And the same thing actually applies down here. So we have a tank that's open to atmosphere. So the pressure of that top of that tank is atmospheric pressure. And we have some sort of pressure P2 right here in this section, and that's what's causing this column of water to be sucked up into the tube, because there is a pressure up here, P2, that is less than atmospheric pressure. And if we go back to lesson A.1, we learned how pressure varies with height. And we had an equation that says that the change in pressure equals rho times g times, I think I wrote it as delta z, and delta z is actually a depth. So as you go deeper into a column of liquid, that causes a rise in the pressure. So I can say that atmospheric pressure, so the pressure down here at the bottom, minus the pressure at the top, is equal to the density of water times g times the height of that fluid. Okay, so I can figure out this height h by figuring out what is the gauge pressure at P2. Well, I can figure out what the pressure P2 is by applying Bernoulli's equation, because Bernoulli's equation involves pressure. So that's my strategy here. I'm going to figure out what pressure P2 is, and then use that to figure out what H has to be. Alright, well, I obviously don't have enough room on this slide, so I'm going to switch slides and make a smaller version of this. So we're going to call this point 1 right here, right as the fluid's opening up to atmosphere. And this pressure is, or this is point 2, and that is where the flow of the air through the tube is constricted. So once I pick 2 points within the fluid flow, I can apply Bernoulli's equation. So let's write down Bernoulli's equation. P plus 1/2 rho v squared plus rho gz is equal to a constant. So, yep, there we go. So let's figure out what that sum is at point 1. So the pressure at point 1 is atmospheric pressure because it empties out into atmosphere. So P atmosphere. So that's going to be the first term. And then the velocity of the fluid is, we're going to call it V1. I think it said assume that the velocity is V1, so that takes care of the kinetic energy of the fluid. We are not changing height, so we don't really need to worry about this term. So we can kind of ignore that term. We can call it 0. Okay, so let's do a similar process at point 2. This pressure, we don't know what it is. We got to figure it out. So we'll call that P2. And then the fluid is, we can assume is flowing at some sort of velocity V2 squared. Or excuse me, V2, which means the kinetic energy per unit volume is 1/2 rho V2 squared. Again, no change in potential energy of the fluid, so we'll completely ignore that third term. Now we can set the sum of these equal to the sum of these, thanks to Bernoulli's equation. And that's what I get here. Okay, not too helpful until I apply the other equation we can apply to fluid flow, and that's the continuity equation. And the continuity equation is going to allow me to change, to express V2 in terms of V1, which is given to me. So when I do that, I've replaced V2 with V1 times A1 over A2. It tells me that A1 is twice the amount of A2. So this right-hand side we can write as 1/2 rho V1 squared times 2 squared. So if I collect my terms, if I collect the pressure terms on the left-hand side and collect the kinetic energy terms on the right-hand side, I have P atmosphere minus P2 is equal to 3/2 rho V1 squared. Okay. Well, I would solve this for P2, but I realize that what was in my equation for pressure versus depth is actually P atmosphere minus P2. So I'm not going to mess around with that equation any further. So this was the pressure versus height equation that we came up with. And Bernoulli's equation and the continuity equation told us this. So I might as well just set these two equal to one another, right? Okay. And this is what we get. The density of water times G times that height H is equal to 3/2 rho. Now, that rho is the density of air times V1 squared. So I can't cancel those terms because they're not the same fluid. But I can solve this for H. And when I solve it for H, I get 3/2 rho V1 squared over the density of water times G. And that is an expression for the height to which that fluid or that water column will rise. So there's our answer for our first example right there. Okay, let's do a second example. And this second example involves an open tank of water. And it has a spigot whose diameter is D. So the spigot over here, we can imagine it is circular, and its diameter is D. It's located at distance h below the water line. And the question is asking what is the volume flow rate Q out of the spigot. So it's asking me how many cubic meters per second are flowing out of the spigot. Okay, well, let's define 2 points in the fluid. So we're going to define the top of the fluid, top of the tank, as point 1 in our fluid. and we're going to define the exit hole out of the spigot as 0.2. And we can now apply Bernoulli's equation and the continuity equation to this fluid flow. Oh, I did something here. Hold on, let me back up. Oops, I didn't want to back that up. Sorry. Let's see here. Oh, I think I'm just writing down that that is some velocity V2. It's actually... Let me back this up. Sorry. There we go. Getting closer. Oh yeah, I want to erase that. Okay. There we go. 0.1, 0.2. And... Whoa. Okay. So that volume flow rate, Q, is equal to that cross-sectional area of that spigot times the velocity at which that fluid is flowing. And I can write that as pi times radius squared, or diameter over 2 squared, times the velocity of that fluid coming out of the spigot. Okay, well, that means I have to find V2. Well, I can find V2 by using either the continuity equation or Bernoulli's equation. So let's try the continuity equation first. The continuity equation says that A1 times V1 is equal to A2 times V2. Well, unfortunately, I don't know A1 here. It doesn't tell me what the diameter of this tank is. And it doesn't tell me how fast this is flowing down, but it does tell us something. We can make the assumption, because this is a big, huge tank, that A1 is much bigger than A2. And if A1 is much bigger than A2, then we can assume that the velocity of the flow at point 1 is very close to 0. So close to 0 that we can ignore it. So we're going to make the assumption that V1 is equal to 0. So the velocity of the flow at this point is 0. That's a very common assumption that you need to make for tanks that are open up to air, especially when, you know, there's like some sort of spigot, then there's some flow out of here, is that the velocity of that flow right up here is 0. Okay. Well, now we have to turn to Bernoulli's equation then in order to figure out what that V2 is. So at that point 1, I've written down P1 plus 1/2 rho V1 squared plus rho times G times Z1. The pressure at point 1, since it's open to atmosphere, is atmospheric pressure. We just assumed from the continuity equation that V1 is 0, so we can ignore the kinetic energy. The potential energy of the fluid is rho times G times H. Okay, let's figure out that same quantity for point 2. So P2 plus 1/2 rho V2 squared plus rho times G times Z. The spigot is also open to atmosphere, so P2 is also atmospheric pressure. We do have kinetic energy in the fluid in the form of 1/2 rho V2 squared. We don't know what V2 is. That's what we're trying to figure out so that we can figure out the volume flow rate. We're going to assume that that spigot is at a height of 0, so we can set the potential energy term equal to 0. And now if I set these two equal to one another because of Bernoulli's equation, I notice that both of them involve atmospheric pressure. So those will subtract out, and I'm just left with rho GH. Ooh, I got ahead of myself there. Sorry about that. Rho GH is equal to 1/2 rho V2 squared, and it turns out that the rho's cancel out, so the density of the fluid is not a factor. And now I end up with V2 squared is equal to 2GH, or V2 is equal to the square root of 2GH. Okay. By the way, I'm just going to make a little aside here, is that This would be the same result that you get if you dropped a ball from height h and you were trying to figure out its velocity just before it hit the ground. It's really an interesting result, right? I think of fluid flow is the same as dropping a ball from a height h. But you get the same result. Interesting. Okay, now I can figure out what the volume fluid flow rate is. Excuse me, volume flow rate is. There we go. Q. We came up with this earlier. It's just pi times the diameter over 2 squared times V2. And if I plug in what we figured out for V2, then I have an expression for the volume flow rate, and that's pi d squared over 4 times the square root of 2gh, and that would be my answer. Okay, well, that was a couple of examples. I know that this has been a long lesson, and it is jam-packed with information. I just couldn't think of a way to split it up into 2 meaningful lessons. So I really apologize for the length of this thing, but it's you really I hope you had a good time with it. Basically, let's put it that way. I find it fascinating. This is one of the most enjoyable lessons I like teaching out of the entire course. So, anyway, I hope you enjoyed it, and I hope this helps you with the problem set. As soon as you finish the problem set, make sure you show it to me so I can give you some feedback. And I look forward to seeing you in class after break. Take care. Bye.